Hello, my name is Oscar Alcantar, and this is video assignment 1, calculating the dot product. Here are our given variables right here, and to find the dot product of vectors v and u, we map them component by component. We multiply the x components and add the product of the y components, and add the product of the z components. This gives us 2 times 1 plus negative 1 times 4 plus 3 times negative 2. Simplifying that out, we get 2 minus 4 minus 6, which evaluates to a scalar value of negative 8. Calculating the cross product. First, we must set up the determinant of a 3 by 3 matrix using the standard unit vectors I, j, and k. And then we want to expand along the top row using cofactor expansions. And then we want to evaluate the 2 by 2 determinants AD minus BC. Okay. J, that equals plus k. Okay. Equals here, right here. Let's go over what we just did real fast. To compute the cross product, we set up a 3 by 3 matrix determinant with the standard basis vectors I, j, and k. In the top row, vector v in the second, and vector u in the third. Expanding by minors along the top row, we break this down into 3 distinct 2 by 2 determinants, but be careful to subtract the middle j term. Evaluating the cross multiplication for each component, our I term yields 2 minus 12. our j term yields -4 minus 3, and our k term yields 8 minus -1. Combining these coefficients gives us -10i plus 7j plus 9k. Written in component form, our final orthogonal vector is -10, 7, and 9. Now, to physically represent the results, we have times u to -8. This is our scalar. And then we have xu is equal to 10. Here's our vector. It is vital to distinguish between the physical outputs of these operations. The dot product yields of a scalar, a simple real number. It acts as an algebraic measurement of directional alignment. Because our result is -8, it explicitly tells us that these vectors are pointing in generally opposing directions. Conversely, the cross product yields a completely new vector. This vector possesses a specific magnitude and directional orientation. Geometrically, this resultant vector is strictly orthogonal, meaning perpendicular, to the entire plane spanned by our two original vectors. Now to explain the geometric relationship dot product and the angle. Excuse me. And this down here, because v times u is equal to -8 greater than 0, cosine theta is negative. Let me write that down. This equals an obtuse angle. The dot product is fundamentally connected to the spatial angle between vectors through the geometric identity v dot u equals the product of their magnitudes times the cosine of theta. If we isolate the cosine of the angle, we see it directly mirrors the sign of the dot product. Because magnitudes are strictly positive, a positive dot product implies an acute angle, and a dot product of 0 proves that vectors are perpendicular. Since our dot product is -8, the cosine of the angle is negative, which definitively proves that the spatial angle between vector v and vector u is obtuse. Now to explain the cross product and area geometric relationship. The area of a parallelogram is equal to the base times height. In this case, our base will be v magnitude, and our height will be magnitude u sine theta. So this means our area is equal to v magnitude of u times sine theta is equals v. Finally, we map vectors v and u tail to tail in three-dimensional space. They define the adjacent sides of a distant parallelogram. The geometric magnitude or length of these cross-product vector is exactly equal to the surface area of this parallelogram. This tracks perfectly with standard geometry. If we treat the magnitude of vector v as our base and the perpendicular height of the parallelogram is represented by the magnitude of u times the sine of theta. Multiplying base times height yields the exact mathematical definition of the cross product's norm. Therefore, computing the length of our cross product vector directly calculates the area enclosed by two vectors. Here is all of the work.